Direction of a magnetic field due to a current carrying wire. Oersted observed that the direction of the magnetic field depends on the direction of the electric current. The direction of the field is given by the right-hand grip rule. Orient your right hand thumb in the direction of the current and then wrap your fingers around the wire. The magnetic field follows the path followed by your curled fingers. So B, uppercase B, is the symbol for magnetic field. To find the direction of the magnetic field at any point on the concentric circles, draw a tangent to the circle at that specific location. The tangent line points in the direction of the magnetic field at that point. There's no component of the magnetic field that points towards or away from the wire. So if you want to know the direction of the magnetic field here, then you would see these circles are all going this way, which means the field at that point is going that way. At this point, it's going that way. Here, it's going that way. And over there, it is going that way. Here's another view of how to find the magnetic field about a current-carrying wire. First of all, don't use this method on a live wire. Make sure it's unplugged. Or even better, use a pencil and assume that the current moves from the eraser up to the point. Grasp the pencil with your right hand and curl your fingers by wrapping them around the pencil. The direction of the curled fingers indicates the direction of the magnetic field. Here, to the left of the wire, like over here, the magnetic field is coming out of the page towards you. On the other side of the wire, over here, the magnetic field is going into the page, away from you. Another way to look at it is the picture below the hand. So here we see these little compasses also showing you the direction of the field at specific points. We can represent an electric field very well on two-dimensional paper. The electric field is, of course, three-dimensional, but it is easily represented in two dimensions. But a magnetic field encircles a current-carrying wire, so magnetic fields need to be shown as three-dimensional to be understood. Somehow we need to show this third dimension on our paper. We have left and right, up and down. So how do we represent the third dimension on a piece of paper? We will use X's and dots. Picture a field line, which is a vector with magnitude and direction like an arrow. The head of the arrow is the direction of the field. If the magnetic field is into the page, you would only see the back of the arrow, which would be the tail feathers. So you'd see the X of the feathers. However, if the magnetic field's out of the page, it means the arrow's flying straight at you, which means you will see the tip of the arrow. Using this X dot notation, the magnetic field around a current-carrying wire can be shown as this. Here, where the field's coming out of the page straight at you, we have dots. Over here, your fingers wrap around into the page. Into the page, we have X's. Here's how the magnetic field would look like inside and outside a current-carrying loop. Using the right-hand grip rule, the right-hand thumb points in the direction of the current, and the fingers curl around and show the magnetic field going out of the page, outside the loop. See how the fingers are coming out of the page on this side and back into the page on the inside. If you choose a different place on the loop, the right-hand rule will still work. So your hand can be placed anywhere on the loop. Again, ensure that if you do this in real life, the wire is not plugged in. An electric current flows into the page. What is the direction of the magnetic field? All right, so here, if you have a circle with an X in it, that means that you have a wire going straight into the page. So you can think of it like there's a wire going into the page. Once again, it's hard to draw the third dimension there, but this is a wire that's coming right out of the page and into the page, and the current is going into the page. So use the right-hand grip rule. Orient your right-hand thumb into the page in the direction of the current. You can use a pencil pointing its tip as well, if that's easier. Then when you curl your fingers around, you see that the magnetic field is in the same direction as your curling fingers, and that is in the clockwise direction. An electric current flows to the right. What is the direction of the magnetic field? So in this case, the wire itself is going from left to right. It's not going into the page. Using the right-hand grip rule, point your right thumb to the right and then curl your fingers. You'll see they come out of the page above the wire and into the page below the wire. An electric current flows in a counterclockwise direction around a circular loop of wire. What is the direction of the magnetic field? Use the right-hand grip rule. So when dealing with a loop of wire, just pick any spot on the wire to do the right-hand rule. So at this point in the wire, the direction of the current is up. That's the current. So point your thumb up, and you'll see your fingers point out of the page on the inside of the wire, on the left side, and then they point into the page on the right side of the wire. A magnet and a compass are placed on the tabletop as shown on the diagram. What is the direction of the compass? Assume that Earth's magnetic field is negligible. Draw one magnetic line of the magnetic field that passes through the location of the compass. So for example, we leave the North Pole, wrap around, and enter the South Pole, and it goes all the way through, like that. So the compass axis will be oriented as a tangent line with the North Pole of the compass facing the South Pole of the magnet. So here, you can see that that magnetic field line is pointing that way. So this compass needle will point the north end of its magnet to the right and the south end to the left. What is the direction of the magnetic field at point P due to the current in this wire flowing straight into the page? First, use the right-hand grip rule to determine that the field around this wire is going to be going in a clockwise direction. So therefore, you just make a tangent line at point P, and you see that that is the direction of the magnetic field at that point. Over here, the field's pointing that way. Here, the field's pointing that way. Here, the field's pointing that way. What is the direction of the magnetic field at point P due to the current flowing out of the page? So here's a wire pointing straight at you out of the page. First, we use the right-hand grip rule. Point your thumb directly at your face, showing that the current's going out of the page, and your fingers will wrap around this way. So therefore, at point P, the field will be going in that direction. A compass is placed above a wire carrying current out of the page. What is the orientation of the compass? Assuming that Earth's magnetic field is negligible. Use the right-hand grip rule, point your thumb at your face, and you see your fingers wrap around this way, which means at this point the field is pointing this way, which means the north side of the magnet is going to face in the direction of the field line, and the south pole of the magnet will point the other direction. What is the direction of the magnetic field at the origin due to two current-carrying wires of equal magnitude? The currents are separated from the origin by the same distance r. First, we start with this wire. So point your thumb out of the page, your fingers curl around this way, which means at the origin, the field points due east. Now, we look at the bottom wire here. So you point your thumb into the page, and your fingers wrap around this way, which means at the origin, the field is going due north. And these vectors have the same magnitude since the currents are the same and the distances are the same. Do a little vector addition to maybe tip-to-tail method. Move this vector over here, draw it like that. Then the hypotenuse is the resultant vector.